Thank you for the introduction, and thank you for having me here. Today's talk is going to be about some recent results that we obtained in collaboration with my former student, Wei-Chen Wu, who has a job at Volion, an hedge fund, but in spare time is still proving theorems. And my collaborator, Yu-Ting Wei at UPenn, we jointly co-advised Wei-Chen. So as an introduction, a lot of the work that I do it deals with high-dimensional statistics, in particular, sort of using a high-dimensional framework to analyze statistical problems under sort of very limited, possibly misspecified settings. And one of the points that I presume will surprise no one is that when you analyze statistical problems in this sort of a more general adversarial, if you will, situation in which the model is specified, and you want to keep track of the impact of dimension of all the parameters simultaneously on the difficulty of the problem, all of a sudden you face a great deal of challenges. And in particular, you need to develop new tools in order to analyze the feasibility and properties of statistical inference. And these are not tools that normally you will learn in sort of classroom or in textbooks, and they're currently being developed. So as an example, I'm just going to spend some time to describe work that has absolutely nothing to do with what the topic of today's talk, which is sort of statistical inference for reinforcement learning. But this is a recent work that I've done in collaboration with Arun Kumar Kuchibhotla, my former colleague at CMU, and it has to do with the most basic, simplest sort of statistical model that I challenge anybody to come up with. And just to drive the point that even in this situation, there is a lot that we don't know about statistical inference in high dimensions. And this model is nothing other than high-dimensional ordinary least square regression. This is sort of a type of methodology that every sort of first-year PhD and master students sort of learn. And I was initially very reluctant to even work on this because I thought there was absolutely nothing really new or interesting that we should be saying about this. I was wrong. Let me start by sort of introducing the model in its so-called model-free or assumption-lean framework. We assume that we are interested in a response variable y, and we observe a set of covariates, x. Y is a random variable, x is a random vector. We make no assumptions on y and x that typically reflect most of sort of data analytic pipelines where somebody comes to you with some data and a regression problem. And you really know very little about the response and the covariates. And here we just assume that they just have two moments. Okay? In particular, we do not make the following assumption, which is what we learn in class. And in many practical situations is unwarranted. We do not assume that the model is linear. The conditional expectation of y given x is a linear function. We also do not assume that conditionally on x, y minus beta transpose x is mean zero and variance sigma square. Again, these are assumptions that we normally use when we cover this type of model, but in practice, they need to be verified. If they're not verified, then so what? In practice, we just go ahead and just use ordinary least square estimators, assuming that, or pretending at least that the model remains linear. And then we compute an error estimator beta hat, which should be familiar to pretty much anyone here, anyone who's taken at least one graduate level class. Beta hat is x transpose x inverse x transpose y. It's the ordinary least square estimators. And we use this quantity in order to carry out statistical inference using traditional tool based on central limit theorem to test for significance or goodness of fit. In fact, beta hat, even though we just use this estimator, is a fine estimator. It's a plug-in estimator for a parameter that is well defined, even in the setting that I just described to you, that where there's no really no structure, no assumptions. In particular, there is a canonical parameter, which is called the projection parameter, which is the sort of coefficient beta star of the L2 projection of the response variable into the linear span of the set of covariates. Okay, so even though we don't assume anything about the model, there is still a notion of well-defined parameter. As long as we have two moments for the response of the covariates, that parameter is given by beta star, and is estimated well. It's in the sense of using a plug-in approach by beta hat. Okay. There is a stat science paper from 2019, which I think everybody should read. And the original title was A Conspiracy Theory of Random Regressor and Nonlinear Random Covariates and Nonlinear Regressor, yada, yada, yada. The title was has been changed to something that's a little bit more relatable for statistical science, but essentially develops a new, referred to classical theory to regression. And that sort of essentially replace, in my opinion, what should be the theory for linear regression that we teach in class. We do not assume the model to be linear. We assume our covariates to be random. And then we carry out statistical inference in these sort of simplified settings. As it turns out, there is a central limit theorem for beta hat minus beta star. The limiting distribution is normal, which means 0, and the variance covariance matrix is so-called the sandwich variance, which is an expression given here. Okay. These are simple proofs. The central limit theories rely on Lindenberg-Fowler condition. There's continuous mapping theory. There's Lansky theorem. All the tools that we learn in our first year PhD courses can be used to sort of prove this. There's a consistent estimator of the sandwich variance. And another lesson that can be learned is that the residual bootstrap, not the residual bootstrap, excuse me, the XY bootstrap, the pairs bootstrap where we resample pairs of X and Y is the right tool to use, but not the residual bootstrap. The reason why this works, it is possible, is that we need to get around the fact that in this assumption link framework, the distribution of the covariates is no longer ancillary. And the target parameter beta star depends on the distribution of the axis, so we need to adjust for that. And the type of adjustment that we need is just to essentially use this type of covariance estimator that protects against heteroscedasticity. So I highly recommend reading this paper. Everything is sort of explained super nicely. And what it boils down to is few modification of the sort of output that are produced when you run the lm command, for example. Okay, so what we did was really liked the paper and decided, what if we redo this theory, but now we keep in mind the fact that the dimensionality can change with that. What I mean by that is that we need to keep track of the impact of the dimension on the feasibility and difficulty of statistical inference. The result that I just told you holds whether we have 3 covariates, 100 covariates, 100,000 covariates. This is an asymptotic result. Of course, we need to be mindful of the fact that the higher the number of covariates, the more complex the problem, the harder the statistical inference is. So how are we going to deal with this? I'm not going to tell you all the details of this work, but I'm just going to tell you what we did. We were able to construct, for a confidence level alpha that's fixed, a confidence set that is in the form of a hyperrectangle. This is a product of confidence of intervals. That's what an hyperrectangle is. Okay, that satisfy the following guarantees. So this is, of course, it's a random set, product of intervals, such that it will simultaneously cover all the beta j's. There should be a star here. This is a target parameter. But probably at least 1 minus alpha minus a quantity that I call the coverage rate that I'm not going to show you. Okay, so he has the right coverage up to this coverage rate. Also, the length of these individual intervals is of order 1 over square root n, which is what you would expect in sort of efficient estimation settings. And everything works out as long as d is little of n. As long as the dimension is smaller than the square root of n, and if you take an asymptotic approach, you want d to be, in fact, much smaller than little of n. Okay? This took a lot of work and was by no means sort of trivial. How do we do this? Well, what we did, we simply use the same approach that is done in traditional parametric statistics. We essentially came out with a wall type construction plus a sort of wild bootstrap to fine-tune the sort of confidence interval. What we found interesting is that statistical inference, at least at this level of efficiency where the size of the confidence interval is of order 1 over square root n, seems to require the dimension to be a smaller order of square root of n. And that's because in this high dimensional settings, when you essentially allow the dimension to now be fixed, or at least when you wanted to account for the dimension, plays a role because the OLS is a bias estimator, and estimating the variance, the sandwich variance itself is highly non-trivial. Again, everything is simple if D is fixed, and we use traditional methods. The moment we step away from this framework and we want to derive a finite sample bound in which the dimension and other quantities are accounted for, we need new tools. Okay? There's more that we can say. More interestingly, if you're actually interested in inference for linear contrast, the form C transpose beta star, you can actually get better results. So D being a little over square root of n is no longer necessary. You can actually, things work out when D is little small order n to the negative 2/3. This is a very recent result that we sort of obtained. It also requires quite a lot of work. Again, this is sort of an example to point out how if you sort of switch gear and you do this type of analysis, you require new tools, you need to develop new bounds. Fundamentally, what we did, one of the steps was to develop a high-dimensional central limit theorem for beta hat, for our ordinary least square. And what I mean by that is that we essentially show the following, that the probability that square root of n of beta hat minus beta star, the L infinity norm of this quantity being less than t is about the same as the probability that the L infinity norm of a Gaussian random vector is less or equal than t, where z is a center Gaussian random vector in the dimension with the sandwich covariance matrix, and this approximation holds uniformly over t. Okay? This is what a high-dimensional central limit theorem sort of looks like in for our work. So let me tell you a little bit more about this. This is going to be the topic of our recent result on reinforcement learning. So at a high level, the central limit theorem is a fundamental result in statistical probability that asserts that the large stochastic system exhibit high degree of regularity, in fact, universality properties. So univariate textbook CLT will tell you that if x1 is w1, w2, wn are independent random variables that have sort of mean zero and sort of variances, then under mild condition, their distribution of the sum normalized by square root of n is about the same as the distribution of a normalized sum of Gaussian random variables with matching moments. That's how you can think about a central limit theorem. Okay? In fact, there is a more quantitative bound known as the Berezin bound that tells the following. There exists a constant c, which is less than a half, such that the following is true. Uniformly over all possible choices of sets that are the form of sort of half infinite interval negative infinity x, uniformly over this class of sets, the probability of membership of your normalized sum based on the wi's, your data, and the normalized sum based on the sort of Gaussian replacement of your data is bounded by a quantity that is of order 1 over square root of n, multiplied by sort of other quantities depend on the sort of third moment of our random variable. Okay, this is known as the Berezin bound. It's a finite sample bound. You don't need to have n goes to infinity. All the properties that are needed in order for us to claim that our normalized sum is close to a Gaussian's are expressed on the right-hand side of this equation. Okay? And what's important here is that it's a uniform bound. It's uniformly over all possible choices of sets. Okay? Okay, this is still a standard textbook result. But what happens when we want to derive a similar result in high dimensions or in dimension D? Okay? When we try to do this, then we're facing a series of challenges because all of a sudden the dimension, the sort of number of moments and property of the moments of the random variable, the geometry, and the choice of intervals now need to be accounted for. And you could have different results depending on your choice of all these quantities. Here is what a high-dimensional central limit theorem now looks like. Let's say you have n independent random vectors in Rd. And let's suppose they're center, and each one has its own variance covariance matrix. And Z1, Zn are Gaussian vectors that I get matched in 2 moments. So the idea is you replace your random variables with Gaussian random variables. And then you look at sort of the normalized sums of these 2 collection of random vectors. And you perform the following task. You define a class of subset C here. And from now on, for the rest of the talk, this class of set is a set of convex sets. It's a large class. So let's say for the class of all convex set, we want to bound the maximal difference between the probability of membership of this normalized sum and the Gaussian replacement to any of these sets. Okay, is this clear what this looks like? Uniformly over all possible choices of convex set, we would like to bound the difference between these 2 probabilities. And so if this difference is small, we can then say that there is a Gaussian approximation to our sort of sum of sort of random vectors. And if it's not only small, but it's vanishing as n goes to infinity, then this effectively gives us some sort of central limit theorem. Okay, but in the sense that we can claim a Gaussian approximation for this normalized sum relatively to this class of sets. Okay, as it turns out, you can have different type of central limit theorem depending on your choice of sets. For the class of convex sets we're going to be looking here, you need to account for a dependence on the dimension that roughly is in the order d to the power to 1/4. If you restrict yourself to the class of Euclidean balls, there is no dependence on the dimension, at least in the leading term. If you look at the class of hyperrectangles, the dimension plays a role, but it's sort of much smaller in the sense of the dependence is sort of logarithmic in D. Okay, so for this class of results, it's very important to sort of choose your target set over which you want to claim some sort of Gaussian approximation. This has been the focus of much recent literature started in 2013 when Chernozukos and collaborator came up with sort of first approximation. It turns out some of these results were already known in the sort of Russian literature, and there's been a sort of a set of string of papers that have improved these rates. So now we get nearly optimal rates. And Arur and I were sort of lucky enough to be sort of part of this race as well. Okay, so all of this that I just told you is just to introduce the type of technical difficulties that we have to face when we are not just analyzing something as simple as a linear regression problem, but we're analyzing something as much, much more complicated as the methodologies that are used in reinforcement learning. Okay, so I'm not going to tell you much about the techniques that we use, but I just want to drive this point once again that if you're really, really interested in analyzing the feasibility and intrinsic difficulty of statistical inference, where you need to keep into account all the possible variables that affect your task, it is important that we sort of develop new tools, and there's really still a lot to be done, even for something as simple as ordinary least square regression. Okay, I'm going to switch gear now. I'm going to talk about reinforcement learning, which is the topic of today's talk. And I just want to say that I am not an expert in reinforcement learning. My student is the one who wanted to work on this problem, and I got involved in it. To me, it was very interesting, the fact, because it's an opportunity to develop sort of new statistical methodologies and results. So reinforcement learning is a collection of tools and theories that describe the dynamics of interaction between an agent and a sort of complex environment. It's been used in a multitude of modern applications, from sort of neuroscience to finance to robotics, autonomous driving systems, healthcare, design of treatments and drugs, and of course, large language models and sort of deep learning methodologies. Reinforcement learning is a fundamental component of why ChatGPT works so well and why sometimes it can reason so well. There are, however, phenomenal challenges from the point of view of statistics in order to understand why this methods really work. State and action space we'll introduce in a moment are prohibitively large. These are sort of statistical and computational challenges. Collecting data can be very, very costly and sort of time consuming. So what is the best way to collect the data? More generally, uncertainty quantification has proven very difficult. As far as we know, there's very little that's been done in order to sort of quantify uncertainty. These models work phenomenally well, but really don't know why they work well, and we didn't know what the uncertainty is of the output that they produce. So we tried to sort of tackle this gap. We just scratched the surface. There's much more that needs to be done. And so what I'm going to do next, I'm going to give you some background on Markov decision processes, and I'm going to tell you about sort of two main results that we obtained. This sort of comes down to high-dimensional central limit theorems for temporal difference learning, which is a methodology that sort of used ubiquitously in this area. Okay, let me just introduce the problem. This is a well-known figure. If you sort of learn reinforcement learning, that's contained in a book by Sutton and Bartow. That's an excellent reference. We started with a environment that can take on one of many possible state space. You can think of this state space as a finite set, even though everything works, even if the set is infinite under sort of very mild condition. There is an agent that operates inside in this environment that, upon observing a time t, a state S sub t for the environment, takes an action A sub t. And after that, immediately get a reward, which is a number between 0 and 1. Okay, so the goal of the agent is to interact with the environment by maximizing this reward. The main decision for the agent is to come up with so-called policy, which is a conditional distribution over the state of over the action space, given the current state of the environment. Now, with all these ingredients, we restart at time t plus 1, where the state of the environment at time t plus 1 transition from given the state at time t and the action taken by the agent at time t. And this is modeled as a Markov decision process. So if I unroll this picture, we will see that at every time t, there are three observables: the action, the state, the current state of the environment, the action taken by the agent, and the reward. Okay, great. One way to quantify the value of a policy, remember the policy is sort of a set of conditional distribution over the action space. One way to quantify the value of a policy is to compute this so-called value function, which is the expected cumulative discounted reward, which is the expected sort of reward that the agent is going to collect over time, appropriately discounted by a factor of a sort of gamma, which is a number between 0 and 1. Okay? And the goal of much of the reinforcement learning methodology is to sort of come up with a good policy and to estimate its value. In practice, however, this is almost impossible, just because the state and the action space are so large that is, there's no other choice than compute an approximation to the value function. And the simplest kind of approximation is the linear approximation. So rather than computing the value function, we compute a sort of linear approximation to the value function. And we do that by essentially creating a feature vector, phi of s, for any possible state S of the environment. And for simplicity, we assume that phi of s is constructed so that its norm is bounded, say, by 1. Okay? And now all of a sudden, we have a sort of something that looks like a linear regression model, where the dimension d that we choose for our feature vector is significantly smaller than the size of the state space. Now, this again looks like a linear regression model, but as really, that's it. It just looks like one. It has no other connection with what I told you at the beginning of this talk. Now, one of the sort of questions you ask yourself, okay, this makes sense. I can now evaluate the value of a function, but I can make it sort of a linear approximation to this. Is this a well-defined task? And so is there a target parameter that we should be sort of considering? And the answer is yes. Just like in the ordinary least square setting, there was a beta star parameter. Now there is a theta star parameter. It's unique. It's well-defined. But unlike the ordinary least square simple example I described to you, even defining these parameters is highly non-trivial. I'm going to sort of skip on a lot of sort of theory behind that. I will refer to sort of really good paper by Tsitsiklis and Von Rooyen for 1997 that essentially says this parameter is sort of a fixed point of a certain equation that looks like A theta star times B, where A and B are sort of a matrix and a vector respectively that are constructed using the sort of stationary distribution of this Markov process over the state space. You don't need to memorize any or remember any of this other than the fact that we have theta star is uniquely defined as solution A theta star is equal to B, where A and B are not computable, of course, because we don't know these quantities. But the point is we have this theta star vector, and now our goal is to estimate theta star. And in doing so, getting the best optimal linear approximation of the value function by a linear function. Okay? There is a canonical algorithm known as temporal difference learning that sort of is used extensively that sort of proceeds in a most natural way. It's a stochastic approximation procedure for estimating theta star that use all the data. And by data, I mean the following quantities. At every time t, we get to observe the state of the environment, the action of the agent, and the reward. Okay, so using this data, we can then compute these quantities here. There is an AT and a BT. They look a lot like the A and the B quantity in the previous slides, and in fact, they are sort of unbiased estimator of those quantities. Okay, so the procedure starts in the following way. We start theta 0 is equal to 0. At each time t, we compute AT and BT. These are computable. And then we just carry out a linear stochastic approximation update where at time t plus 1, the estimate of theta, is equal to the estimate of theta at time t minus a quantity that is proportional to the sort of error between a t theta t minus beta t. The proportionality is a sort of learning rate. This is a quantity that we assume to be decaying polynomially as in t. Okay, this is kind of looks like as SGD type of an update. It's somewhat fairly standard. In fact, we're not just going to use this. We're going to take an average of all the updates up to a time capital T. So we're going to run this procedure for time 0 up to time capital T, and we're going to take the average. This is a standard methodology used in SGD settings. It's the sort of Polyak-Rupert average TD as sort of good reasons to, there are many good reasons to use this estimator as opposed to theta t. Is this clear? So we have a target parameter, and we have an estimator that people use extensively. At this point, what we would like to do is to study the estimation error. The difference between theta bar t, this is the average TD estimator, and theta star. This is the unknown target parameter. And we do this in two ways. We establish high probability bounds for the norm of this difference. I'm not going to tell you much about this. And more importantly, and this is the harder part, we're going to construct Bayesian bounds for the quantity root capital T. Capital T is the number of observations we have, times delta T. Okay? And we analyze two settings. The first one is, or at least looked to me as soon as I start working on this problem, just plainly dumb. Just because we assume that the data are independent. The data observations are absolutely not independent. I couldn't understand why anybody would even consider this, but then I realized that a lot of the literature was actually focusing on this part, where at every time t, we essentially get an independent sample from a stationary distribution, and we ignore any Markovian dynamics. That turns out to be also already quite difficult. But more recently, we're succeeded in sort of actually accounting for the presence of a Markovian dynamics. So we're no longer assuming that at every t we have sort of independent samples, but we sort of allow for Markovian trajectories. Okay, and I should just point out, just like in my OLS example, if D is fixed, if we don't essentially take into account the impact or dimensionality of all the other parameters, there is already a set of beautiful results that obtained in 2015 by Ford that gives central limit theorem for the quantity of interest both in independent and dependent samples. And there are sort of there's a quantity asymptotic variances, lambda star and lambda star tilde for independent and Markovian samples. So we already have a sort of an idea what our results should look like. And the question is, can we look at, can we obtain similar results now in a more challenging situation where we want to keep track of all the parameters, in particular the dimensionality. This is our contribution. Is just one of many beautiful. Ours is not beautiful. These people wrote beautiful papers. I didn't want to, but there's a lot of sort of great work that's out there, written by at a sort of incredibly fast pace by many researchers, and so ours is just one of a contribution among sort of many others. So just to summarize, this is what we would like to do. Is to establish high-dimensional central limit theorem that says that uniformly over all possible choices of convex set, that's the MATCAL C is the set of convex set. We would like to bound the difference, the probability that our rescale TD error belongs to that set minus the probability that a Gaussian random vector with matching dimension and first two orders belong to the same set. And in particular, the variance of Z should be the asymptotic variance that is known in fixed dimension. Okay, and like in the example involving linear regression, we would like to be as explicit as possible the dependence on capital T. That certainly has to be there, but also on sort of the dimension and other quantities that are affecting the difficulty of the problem. A major challenge here, though, is that our target quantity is not a linear function of the data. This is not a normalized sum. To be fair, not even in the ordinary least square regression example, we actually had a sum. We had to sort of linearize, use sort of efficient influence functions. But here, it's even more complicated. So we're essentially trying to get a central limit theorem in high dimension over the class of convex set for independent and Markovian data when we don't have linear functions of the data, but we have complex functions of the data. Okay, so I want to tell you just the results and sort of point out, comment on some of the challenges. So we assume the setting that I just described to you, and in particular, it's important that we have a polynomially decay step size, eta t, which is equal to eta 0 times t to the negative alpha, where alpha is between 1/2 and 1. We're not going to define a finite sample covariance matrix. That is the covariance matrix of our error at time t. This does not match the asymptotic covariance matrix, but it is a covariance matrix for our target quantity. And our first result says that we're actually able to get a high-dimensional central limit theorem that looks quite honestly ugly. But there's not much we can do about that. At least we're not able to make it pretty. The leading term of this high-dimensional Berriesian bound has a dependence on t. Think of t as the sample size, order negative alpha over 2. This, of course, is worse than the negative 1/2. And there are sort of quantities here that depends on the dimension and the sort of distribution of the data. Gamma is the sort of the variance covariance of A theta plus b. There is a term here that I've told you much about that is a smaller order. It's square root of d times t to the negative 1/2. So it's not the leading term in this approximation. Okay, so this is our first result. And then choosing alpha to be equal to 2/3 under additional mild condition, we're actually able to obtain our final results where now we are going to use the true asymptotic variance, not the sort of a finite sample asymptotic variance, and we're able to obtain an approximation that is square root of d times t to the negative 1/3. Okay, and that I don't know if probably doesn't look very much to you, but we were really happy about that. Yes.
What
Oh, the class of sets, the convex sets. Convex set. Set of all convex set. The reason why we choose convex set, thank you for the question, I should have said it sooner, is because if you want to construct confidence sets for high dimensional parameters, that's a natural class you want to be using. Ellipsoids, hyperrectangles. I think that's, it's kind of hard to think about a confidence set that's sort of something that's not convex. But so we were happy about that, about using this class. A few comments about this. This is the sharpest rate that is currently known. It improves on a rate of t to the negative 1/4 that was obtained while we were working on this problem. So everything that we're doing, I know there are groups working on that as well. So it's nerve-wracking, and I can tell you. And so there is a really good competing group that obtains sort of this lower rate by sort of using a somewhat different kind of analysis, not as tight. We think our rate is sharp. We're working on that. It's not a proof, but there's good reason to believe that. And our analysis is really a very, very sort of careful application of a general Bayesian bound for nonlinear statistics that was established recently in 2021. The reason why I'm saying this is that we really are doing, there is one result that exists in the literature by Xiao and Zhang that everybody uses, Samsonov and company and us. And the name of the game was to be very, very tight in a series of calculations. Yes. Alpha, yes. Alpha is determine the speed of the learning rate for the algorithm itself. It's not a quantity that has anything to do with the data. It is a quantity that sort of describes how the algorithm works. And so we can choose that value of alpha. It's not clear what the value of alpha should be a priori. In fact, over this first result, we say that you don't have to choose alpha. Here is the rate for you. The choice of alpha that leads to negative 1/3 is that if we want to use the asymptotic variance covariance as our sort of target. And to be honest, it's kind of a miracle that everything works out at this rate. We were not expecting that. But this choice of alpha appears to be the right one. And let me show you some simulation where I can give you the sort of a distributional error of between the normal and our sort of normalized TD error as a function of alpha. And so you can see here that alpha to the power of 2/3 down here is the one that gives us the sort of slowest error. Alpha equal to 1/2 is what Samson and the other group use. Seems, according to this simulation, to actually give us a worse error. We don't know why other choices of alpha seems to be giving the same values. We have no idea. This seems to be hard to prove for us, but we were happy that at least in simulation this got confirmed. I know I have like 5 minutes, so I want to tell you 2 things at this point. Maybe I'm only going to tell you one. The result that we just obtained made us really happy, but is really of no use for statistical inference, simply because we do not know how, in order to construct a confidence interval, you only need to have a reference distribution, in this case, the normal distribution, a pivot for the problem, but you also need to be able to estimate the variance. So the Bayesian bound I just gave you is a Bayesian bound where we assume that we know the variance. So we need to estimate the variance, which is highly non-trivial task. So whenever you're facing a highly non-trivial task, what I suggested to my student, and this was my contribution to this result, was like, why don't you try the simplest thing? Why don't you try the plug-in estimator? You know that it's not going to work? He said, nope. And so he actually did just a plug-in estimator. In fact, not just a plug-in estimator, it's sort of a methodology that can be done sort of in an online manner. To be completely honest, this is not very practical. The space complexity of these procedures is d to the 4. So we cannot really use it in super high, in large dimension. But what's important here is that it's still more efficient than the current state-of-the-art methodology for uncertainty quantification, which essentially is based on multiple repetition of the process that I just described to you, combined with the multiply booster. Essentially, you kind of bootstrap trajectories, and you have to do it a very large number of times in order for you to be able to get uncertainty quantification for this. So it's, even though the computational is not great, it's still better than anything that people have been able to come up with. And the good news is that, and that's actually, this is the miracle, is that when we estimate the variance, contrary to what we observe in the ordinary least square, where estimating the variance is harder than getting a central limit theorem, here we end up with essentially the same rate, t to the negative 1/3. This is a situation where all the stars align. We were not expecting that, but amazingly, estimating the variance does not hurt the rate. So t to the negative 1/3 is still the rate for statistical inference. So how do we use this? I'm going to skip some of these comments. How do we use this? Well, now we have a sort of Gaussian approximation. We have a sort of way to estimate the variance. And now because this guarantee holds over any choice of the convex set, we essentially are able to sort of construct a sort of confidence intervals by sort of adding to our estimator a quantity, a random quantity that's a Gaussian that has sort of the estimated variance. That center is 0 has estimated variance. And this is sort of guarantee to give us the target coverage. Of course, we need to pay a price here. The coverage is only guaranteed up to square root of d t to the negative 1/3 rate. But we're quite happy about that. Again, what's important is that the guarantee is uniform overall possible choices of convex set. And one of the questions that we're currently working on is, do we really need convex sets? The class of all convex sets. That's very, very large. For example, it has infinite VC dimension. If you want to measure that in terms of complexity, in terms of sort of Gaussian complexity that's measured by sort of the surface area is d to the 1/4, which is large. So rather than use the focusing on convex set, we can just look at hyperrectangles, which is one type of convex sets that are especially useful for statistics, because once you have a hyperrectangle, you have, which is a product of confidence intervals, we have simultaneous confidence intervals. So we're actually working on that, see if we can get something that's sort of slightly better in terms of sort of dependence on the dimension. But the point here is that even with this, for statistical inference purposes, we are at this point getting the best rates out there, despite really hard competition by sort of really good people. It's 12:15, and no, this will take a whole lot longer than that. I just want to tell you this. Our latest result is that the extension of the results I just told you about to Markovian samples, which was really, really far from trivial. I need to applaud Wei Chen, my student, for being able to work so hard on this problem while making gazillion of money, working at an hedge fund. You can tell that he really loves statistics. But essentially, so we're able to sort of prove similar results for high-dimensional Bayesian bound for Markovian data. As far as we know, this is the first Bayesian bound for some of martingale differences in the Wasserstein distance. It can be used, we believe, as a tool to analyze SGD or stochastic approximations. Along the way, we're able to prove a sort of matrix of the inequality for Markovian data, which we are very proud of, just to find out that after we posted the paper that a graduate student at UT Austin, where I am, just across from Speedway, had published like a month before a paper with the same bound. We have slightly different proofs, but it's actually the same bound. So he got there first. But we're very proud of all these results. And sort of we're working now on a series of extensions. But the point is, once again, if you're really interested in sort of in feasibility of statistical inference in these high dimensional settings, you really ought to develop new tools that are not contained in textbook. Okay, thank you.